Okay, so now we're going to be doing a homework 1 part D. Again, I have this piece of paper right here that literally just has the question on it, so I can just read it from there. But basically the question says, divide the CSTR into 20 smaller CSTRs in a series to mimic a flow reactor with back mixing. We'll want to simulate and plot the concentration, the temperature, evolution of those 20 tanks over 2 minutes, starting with an initial concentration of 0.5 molar at a temperature of 330.5 Kelvin in each tank, and then we maintain a constant inlet concentration and a temperature of 1 molar and 330.5 Kelvin. So, from that, we're going to be taking what I did in part B and adjusting it to help us be able to simulate this. So, first and foremost, we're going to have a certain number of tanks, so I'm going to add that n is equal to 20. And then for me, I'm going to get rid of these because that's not going to be necessary for this. And then we also will need to do, I'm going to change this to be total volume, and then this is going to be V total divided by N. We're keeping all of our other initials the same. And then we want the T end to be, in this case, 2, because it's going to look at the evolution of those 20 tanks over 2 minutes. So we're going to be having that. And then I'm going to be changing what this initial concentration is to 338.5 Kelvin. And then on top of that, what we're going to do is we're actually going to do NP dot full. I forgot another thing. And then we're going to have it be 0.5 N. And then we're doing the same thing down here for this one as well. NP dot full 338.5. And this is just going to make sure that we're distributing it out amongst however many, like that number will be distributed out, in this case for concentration 0.5, in the case of the temperature 338.5. That's going to be distributed across, in this case, 20 tanks, because our N is identifying how many tanks we have in the series. That was bothering me. Okay, now we have this set up. Let's come down here. So what we're going to do next, we're going to change this vector. We're going to do an NP dot, an NP dot split, as we want to split that into subvectors. So we're going to do that, and there's 2 of them. And then from there, we'll keep our K. And then what we're going to also need to do, since if you remember from part B, I had showed how we can get the material balance and the energy balance. And essentially, it's going to be that for the material balance, we're going to have Q divided by V times the concentration going in minus the concentration of that tank is all minus the K times the concentration of that tank. Now, if you remember, there's technically 2 cases. There's that equation for the first tank and an equation for the rest of the tanks in that series. And that's going to apply not only for the concentration, where I'll have to go and rewrite out this equation specifically for the first tank, and then after that, the tanks for the rest of the series. But then the same thing will apply with the temperature, as if you remember from the energy balance, we were able to move some stuff around to get dt over d temperature over d time, or get dt d uppercase T. So then we have this equation here, which we can then also make it to where we have to adjust it just to look at for the first tank, and then for every other tank in the series. So I'm going to go and do that now. So what I'm going to do is we're going to do that, and then we'll do this, and then I'm going to do, let me make that capital T, excuse me, and then D, N, so then I can be able to write this correctly. Let me go and I'm going to call this CAN, and this is going to be CA, and it's going to be at the initial concentration, and then same thing for our K. oh my gosh, and for this concentration as well. And then we can go over here and then but this time we're going to be looking at the concentration as it goes from 1 actually, excuse me, that's supposed to be 1 and this is supposed to be -1. Then we're gonna have this and that, and then let me go down here and then take this whole equation, this behemoth of an equation, put this here, and then I'll call that Tn, and then we're going to have it be 0. This will be 0, that will be 0, and then the last thing we have to change is this temperature here to also be at the initial state. And then we're gonna go down here, oh no, there we go, and do that. And then we're gonna do what we did up top for when it was the rest in series, where we're going to do, oh, nope, this minus why do I keep doing that? There we go. And then we're just gonna go and do this for the rest of them. And then down here at the return, we're just gonna have it return all 4 of those values. So it's going to return, which we need to do DC naught, DCN, DT naught, DTN. I might have to just go back through and save those funds first. Let me do this, then that. What is the problem? Why is it doing this? Okay, give me 1 second. I'm gonna check and see why it is giving me this error. Try to figure it out. Okay, so I realized why it's giving me this issue. It's because I accidentally flipped these two. So I need to actually go here and put the n in front of the variables. So my bad. There we go. Now this should, yep, there we go. Okay, my apologies. That was my fault. And then let me quickly go back here because I think I want to double check. So yeah, I have, so this CAN and TN, we're going to go and define those specifically. As for the CA or concentration going in, we know that it needs to maintain a constant inlet concentration of 1 molar. So that we're going to have it return as 1 in respect to time. So then this variable here is going to change when I do that. And then temperature, we're going to have it also come back with 338.5, as again, it says that it wants to maintain a constant inlet concentration and temperature, in this case the temperature being at 338.5 Kelvin. So we're going to have it return that number as well. So before I do that, I want to double check to make sure everything here is okay. I'm glad I double checked over here because I forgot to, I had this the wrong way, And then I'm just peeping this now too. I also had these wrong because I didn't put the little dual decimal points to help make sure it's getting the entire line essentially, or in the array. And then, so let me double check down here. There's a lot of colors going on, so my eyes are kind of tripping out right now. Okay, so I wrote these ones wrong as well. This needs to be on this side. So one double checked and -1, and then 1, that. And then these also need to have these as well. Let me go back through here and do that. Okay. And then I completely forgot. We also are going to be using MP dot, oh my gosh, why did I make those capital? MP dot R underscore, so we can split this into multiple little sections, essentially, because MP.R is just slicing the objects to concentration along just like an axis. So that's all this is going to be doing. Let me do that. And then I'm going to go back right here because I just like doing that for myself. Define. What do we call it? CAN with respect to T. And it's going, nope, that is not how you spell return. We're going to return the concentration as 1. And then we're going to define, oh my gosh, temperature in with respect to T. And that is going to return 338.5 Kelvin. So we'll hit Shift Enter there. And so then we're going to come back down here, and then I'm just going to go for everything to look so that we know where everything is pulling from. I'm going to add those 2 in there. Perfect. So now we can go and we're going to change this resolve IDP. We're going to keep it redo, dense output true. We're still having it be from 0 to T end, and we're still having it be this right-hand side. But what I'm going to do is I'm going to change this part here to actually be looking for the vector. So I'll just put it here, I think, maybe. I'll have it be MPR underscore. And we're going to be doing this for the initial concentration and the temperature. The initial temperature as well, because again, we're pulling from 20 tanks, all will have 0.5. 20 tanks will all be at 338.5, and we need those as the initial variables for the dependent variables. In this case, the concentration and the temperature are the dependent variables on the time, which we've defined as whatever 0 to T end is. And we want to, use all the dependent variables, the initial dependent variables of all the tanks, in this case, CA naught and T naught, across a 20 tank series for that. So with that, Shift Enter, Shift Enter. Should be good. Shift Enter. Oh, what is going on? Must be one dimensional. Okay. Give me one moment. I'm going to figure out why it's giving me this. Because I think maybe what part is... Okay, give me one moment. I'll be right back. I'm going to figure out what's going on with this, because this should be it, I thought. Yeah, okay, give me a moment. I'm going to figure out what's going on here. Okay, so I figured out I'm spacing out, I guess, because this is literally supposed to be the vector, because I literally already went and defined the dependent variables, setting both of them to the vector Well, in this case, let me actually make this vec not. So yeah, my apologies. I don't know why I was spacing out here. Oh, and what's going on now? How is this not callable? Do I need to go back up and do it from the top again? Shift. Okay. What part of this isn't? What part of this isn't wanting to DCN? DC not DCN, DT not DTN. So I gotta. We're gonna see if we do this first, if that might work, because I don't know what. Nope, okay, well, give me a second. I'm gonna figure out why it's doing this, because, yeah. Okay, give me one moment, I'll be right back again. Okay, so I'm back. It's because I don't have brackets, because this type of thing, the mp.r underscore, I guess that's what that dash technically is called, needs brackets. And I just didn't. I used parentheses. Python can be very, 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 very frustrating because it could be simple as just having to need brackets versus parentheses, but it's okay. It's okay. We move forward. So now that we have this defined, we have the solve IVP going to get us the resolution. Now we're gonna have our make our T plot and for time, and then we're gonna make our concentration plot and temperature plot from this. So we have T plot equal to np dot line space 0 to T end, and then I'll change this up. I'll make this maybe like 101 or something, and then from there, let me go here and title this just so then I can know what I'm calling them. And then we're going to do np dot split because we want to split up this T plot that it's going to make because we have the two dependent variables, concentration and temperature. 2, and then the axis will be, no, but I did not mean that, minus. Axis will be equal to 0. And then, there we go. So that fixes that because that error was bugging me. We're going to have our fig equals make underscore subplots. And then now what we need to do is we need to make a for loop so that way then we can loop it for the number of times for the iterations of like how many tanks are in the series. So for here, we're going to take, can I think, no, I didn't, no, okay. I just wanted to copy this, please. There we go. Oh, so much hair everywhere. Okay. And then we're going to have this be our C plot, which we're going to have it be for the number of iterations up until a certain point. Row and column is fine. And then what we're going to do is we're going to have a function, and then we're going to have it be CA for concentration, and then it's going to be whatever the number of iterations it's going for. All right, and then we're going to copy this and then do this for the temperature plot. Change this to capital T, and then change this over here to T as well. And then let me get rid of, oh, nope. Okay, there we go. Let me get rid of these two, and then this should work. I don't Okay, that's not exactly what we would like to see. Um, let me see if I change these. Oh, no. If I change this. Nope, didn't want that there. If I change this to the other side, if that does anything. No, okay. Yeah, I was right about having those on the other side, but... oh my gosh, stop it. Okay. Let me... Oh my gosh. There we go. Okay, shift enter, shift enter, shift enter, shift enter, shift enter, shift enter, shift enter. Okay. Something I missed in my code. I figured out update layout. I have the scatter. We have the X being the time, and for the concentration, it is C plot, which we have to find up here from splitting the T plot up because there's two different dependent variables, and we made sure it's C plot, concentration plot, then temperature plot. That's being split as well for that vector, cross for here. And then we have CAN and TN defined. That's good. Those are good. Something else I missed over here, maybe? V total is equal to divide by N. Ew! Oh, I forgot to divide this by N too. So we have to divide UA by N as well. And maybe, no. I mean, good, I catch that other one, but still. Let me see if I put this inline in the for loop, if that does anything. Nope, okay. All right, give me a moment. I'm gonna try to figure out what's wrong with my code because it should not be appearing like this currently. So give me a moment, I'll be right back. Okay, I think I figured out what it is. And I was just messing around with this because I thought, oh, I need to switch the I around. I forgot to put these two commas here. But it still is doing that. What is going on with this? I'm gonna just redo everything again to make sure it's starting from the start, in the beginning. Okay. Gosh, so much hair. Let me see if I do it past 2 minutes. Let's just see if that changes anything. I mean, it just elongates that, showing that it's going to steady state. I wonder why it is doing this. I don't like that. Let me go back to 2 minutes for now. All right, give me one moment. I'm gonna see why. Oh, it's putting them on the same graph. Okay. I see what the issue is. I forgot to put it in a second column. There we go. Oh, okay. We're here. We are finally here. Because why? Why was it doing that? It's so frustrating. Let me... Sorry, I'm just playing around with the height right now because I want to kind of like see what I kind of like. I like that. Let me see if I want to increase the width at all. No, okay, we're gonna go back to the, yeah, okay, I like that. All right, so now, finally, we have our concentration and temperature profiles. Here on the left, we have our concentration, and here on the right, we have our temperature. Now, what I'm gonna do is I'm going to just show them at different points when it's at the initial tanks, somewhere in the middle, and the very end. So when it's at the very beginning, we know that it originally started at 0.5 concentration, and then an inlet of 1 mole happens. So therefore, that's why this concentration is jumping from 0.5 up to 1, because it's representing how through that first tank, it's going from 0.5 molar to 1 molar. And as for the temperature, it says 338.5. And as we can see here, this is the 338.5, initially dips for a moment, and then it jumps up just because when you're increasing the concentration, you're then increasing the reaction to go faster. And if the reaction is going faster, it's going to cause more exothermic reactions. Therefore, the temperature is going to increase. Hence why this temperature jumps, why it initially kind of dips down for a second, but then immediately jumps up as that concentration increases. So then if we go to like, oh, I don't know why I just did that. If we have it go somewhere, let me please pick somewhere in the middle, please. Thank you. Nope, I did not want that. Let me do this. As we can see here, initial temperature, initial concentration in the tank. Now we're seeing, at tank 11 in this tank series, as time went on, it was staying around the 0.5, kind of was decreasing a little bit, but then once it hit tank 11, the concentration went up a bit from that 0.5, because this 0.1 is rippling through the tank series, and then it immediately goes down to 0, hence showing that it's then going kind of into a steady state, because at that point then we said we wanted to maintain a constant inlet concentration of 1 molar. So once the system initially has that change from 0.5 to 1 molar, it's then going to start to level out, as we want that to then be we're going to have that be the constant inlet concentration coming into the tank series. So then we would want it to eventually go to 0 to show that it's now going through kind of a steady state, or it's going to a steady state. Not approximately a steady state, because 338.5 just being simulated here is the kind of closest we can find to it being steady state without it kind of starting to break the graph and other things like that. And then again, the temperature in that tank is reflecting the same thing, whereas we see here that when it kind of gets to around, when the temperature starts to increase after like 0.5 seconds, we see here at 0.5 seconds, the temperature starts to increase too, because again, as the concentration is increasing, you're going to have more concentration to help make that reaction happen quicker, which is then going to cause more exothermic reaction to happen, which is then going to increase that temperature, hence why that temperature is jumping up. And then we'll lastly look at the last tank in the series. So as we can see here, this last tank in the series, it also still has a little like bump up, a little like it feels a little bit of that concentration from the switch from 0.5 to 1 molar, but it's not as significant as tank 11 was or as tank 1 was, or that first tank in the series. And that's just because as that concentration change was going through the tank series, every tank before the last tank is using some of that material. Therefore, it's actually going to lessen how much the last tank is actually going to have a, in this case, a major jump in its temperature due to an increase in concentration, fueling that reaction to happen quicker, giving off more exothermic reaction, therefore increasing its temperature. Hence why we kind of see it also kind of going and like only spiking up a little bit compared to what happened before. But yeah. So, and then again, it kind of teeters down to where it goes to a steady state. And that's why eventually all of them do kind of flatten out. And it's just these first few tanks where it has that really major hit of that concentration. As the other ones, you can kind of see as the concentrations kind of go on, they kind of start to like stagnate a little more. And they kind of just kind of slowly start falling less and less of like having a high concentration spike. And then their temperatures also reflect that as well. And if I were to increase the time, we can just I'll go to 4 minutes. Again, it's showing that, after they have their initial jumps, they then settle out to a steady state. So that's kind of the concentration and temperature profiles, how they relate together and how they relate specifically in this case over when I showed you, when I had it at 2 minutes, how it goes from a starting concentration of 0.5 and a temperature of 338.5 Kelvin. And then it, as you change that inlet concentration to be 1 molar and you still keep that temperature, what that kind of looks like. Because again, as we can see, all their concentrations do kind of, teeter out over time. But yeah. And then I'm just going to quickly, which one is that? That's T6. I'm just curious to kind of look at T6 really quickly. Yeah, okay. I just wanted to, just curious for my own knowledge. But yes, okay. So that is homework 1 part D. Thank you.